We conclude chapter 7 with our fourth video, where we will get a couple of new reactions to put in your wheelhouse from chapter 7 in addition to the tautomerization, and then see an introduction to multi-step synthesis. So a big focus here from video 4 is different ways that you can add hydrogen to alkynes. So let's say I wanted to take an alkyne all the way to an alkane, right? Just completely nuke those pi bonds there. Yep. You do that the same way that you would hydrogenate an alkene, right? Add hydrogen using a palladium on carbon catalyst. Yep. And that's going to take your alkyne all the way to the alkane in 2 steps. It's difficult to stop at the alkene, but it can be done. Yep. If you used hydrogen plus what's known as a Lindlar catalyst, that will take your alkyne, hydrogenate it once, right, at a single pair of H2s, and stop at the alkene. Okay, because the Lindlar catalyst is what's known as a poisoned catalyst. Okay, that means it's partially deactivated. Makes it harder to add hydrogen to the triple bond, and it's only going to do it once instead of twice. Okay? Again, if I use palladium on carbon here, it's going to go all the way. But if I use hydrogen and the Lindlar catalyst together, that'll take me just to the alkene. Okay? And this Lindlar catalyst is a combination of palladium, lead acetate, quinoline, and calcium carbonate. For the purposes of my tests, you just have to know Lindlar catalyst and hydrogen will take you from an alkyne to an alkene. If you're doing the Lindlar catalyst, it's going via a Syn addition. Okay? So it forms a cis product specifically with regard to your alkene. Right? Same thing, the hydrogen has to sit on the surface of a catalyst. We saw that in chapter 6 with hydrogen and palladium on carbon being a Syn addition. So we have a Syn addition here again when you have hydrogen and Lindlar forming a cis alkene. Right? Why is that? As we just mentioned, it has to work just on one side. So what if I wanted to do an anti-addition so I could get a trans alkene as a product? Well, there is a way to do it, but it's a little bit different. Okay? It's something that's known as a dissolving metal reduction. And a dissolving metal reduction will take an alkyne to an alkene via an anti-addition, therefore forming the trans product. And this is accomplished by using either elemental sodium or elemental lithium, choose one or the other, in liquid ammonia, and it's done at -78 degrees Celsius. And this takes advantage of the fact that these alkali metals react more rapidly with triple bonds than they do double bonds. So what does this mechanism look like? Well, the steps are listed out here in slide 58 and then shown on the next slide, 59. Okay? Note that this only works for internal alkynes. Okay, so you can't do this with a terminal alkyne. But if you have an internal alkyne, you want to take it to a trans alkene, you do the dissolving metal reduction. That takes an electron out of the s orbital from your metal, transfers it to the sp carbon of the alkyne. That makes a radical anion. Okay, so radical means it has a single unpaired electron. Anion means a negative charge. That's a strong base, so it pulls a proton off of ammonia. Now you see why the liquid ammonia is necessary. That makes a vinylic radical. Okay. Then we transfer the electron from sodium to the vinylic radical to form a vinylic anion, which pulls a proton off of a different ammonia molecule and forms a trans alkene. Radicals aren't covered until chapter 12. So while I want you to be aware of this mechanism, it won't be explicitly tested. What I do want to draw your attention to, just to set the precedent for later on, notice the single barbed arrows here. Right? See, this over here, when we move 2 electrons, we use a normal arrow with 2 barbs, right? 2 ends, 2 hooks, right? But here it's just a single hook when we move a single electron. So you don't have to know that mechanism right now, but in case you were curious how it happens, it's shown here on slide 59. This has to be a trans alkene, right? And it occurs via an anti-addition due to the stability of the anions, right? We want these things to be trans to one another because the electron clouds are larger, making it more stable. So the takeaways so far: know the 3 different ways to hydrogenate an alkyne. If it's hydrogen and palladium on carbon, it goes all the way to an alkane. If it's hydrogen and Lindlar catalyst, it goes to a cis alkene. And if it's a dissolving metal reduction, it goes to a trans alkene. Jumping back a couple slides here, right? You do not need to know the mechanism. You do need to know the reagents necessary for an anti-addition for that dissolving metal reduction. So that brings us to synthesis, right? Which is really what organic boils down to at the end of the day. Can you do synthesis? Will be a big emphasis for test 4 in the final exam. So we're going to get one more reaction before we see examples of synthetic applications. Thinking all the way back to chapter 2, different electronegativities of carbon, right? The higher the S character, the more electronegative something is. So something that's SP, right, 50% S, 50% P, is more electronegative than sp3, 25% S, 75% P. More electronegative, right, means that hydrogens attached to sp carbons are more acidic, okay, relative to the others. Still not something I would call an acid if I just put it in water, because water has a pKa of 15.7, excuse me. But here our alkynes, right, have pKa's of around 25 if it's a terminal alkyne, so it has the hydrogen. Okay. So that puts us, right, somewhere between water and ammonia in terms of acid strength. So what can we do with that? Well, if I use an alkyne and a hydroxide ion, it's not going to really do anything because that alkyne is not a strong enough base to do anything. But if I use an amide ion, NH2-, that's a stronger base, okay? Meaning that it can pluck a hydrogen off of a terminal alkyne, forming ammonia and an acetylide ion. Notice the difference in the equilibrium arrows on the top and the bottom here. Here, the equilibrium is lying to the right, the formation of the weaker acid. So that's what I'm going to use, the amide ion. You typically see it in the form of sodium amide, NaNH2, right? Plus a terminal alkyne will deprotonate that hydrogen off of the alkyne and form the acetylide ion. That acts as a nucleophile, and we can use it in synthesis. Yep. Take this with a primary alkyl halide, right? Here I've got an electrophilic carbon with a delta positive there, right? Because bromine is electronegative. That makes this carbon an electrophile. Negative charge here, this is a good nucleophile. And this can come in and attack, kick off bromine, and I have extended my carbon chain. And forming new carbon-carbon bonds is a very important process in organic chemistry. It's not super easy to do. And this is a great way to do that. I have to say I want to extend my carbon chain and then take this to an alkane, right, to make heptane. Then I could treat this with hydrogen and palladium on carbon, as we just saw. Here's the mechanism, right, which I was talking about before. And this is known as an alkylation reaction. We added this alkyl group right here to a species. And again, bromine is electronegative, giving this carbon a partial positive, right? Therefore, it's acting as an electrophile. Negative charge here allows us to act as a nucleophile. And then again, it attacks, kicks off simultaneously because that carbon couldn't have 5 bonds. And I've formed a new carbon-carbon bond right in here. Overall, it would be a 2-step reaction. Take a terminal alkyne, treat it with sodium amide to deprotonate and form your carbanion. Then treat this with any primary alkyl halide. So I wouldn't use secondary or tertiary, just primary here. And then I can extend my carbon chain if I want to put on 2 carbons, 3, 4, 5, however many I want. And so this would be your first synthesis, making heptyne from pentyne using sodium amide and ethyl bromide. One tip for synthesis, right, is kind of what I was just alluding to. You can convert a terminal alkyne into an internal alkyne of any length. You can add any number of carbons that you want to, just by choosing the right alkyl halide. And so you change, jumping back to slide 70 here, change this number of carbons, that determines how many you've added. So that takes us into multi-step synthesis, which is a cornerstone of organic chemistry and a really good way to review the ideas from chapter 5, 6, and 7. There are a couple of factors that affect a synthetic design if you're making something in the lab. Time, cost, and yield. The time it takes to do a reaction. The cost, you want to use the cheapest reagents possible to maximize your profit. And the yield, you want your individual steps to be as efficient as possible because nothing has a 100% yield. At this point, because you're not as familiar with time and cost, right, we're really focused on yield. And we want to have these reactions be accomplished with the fewest steps possible. Because if no step has 100% yield, every step you add reduces the overall extent of the product. So when you're designing your synthesis, keep in mind you want to take as few steps as possible when you're coming up with your final answer. So the rest of chapter 7 goes through and discusses individual synthetic applications, synthetic designs, and examples to come up with them. So what's the focus? The first one that you're given is discovering how to take 1-butene and make a ketone over here. So you think to yourself, I'm going to work backward. Consider my ketone that I have here on the right, and then you do, remember this term from earlier, a retrosynthesis or a retrosynthetic analysis. So you see that it's a ketone. You ask yourself, how do I make that? Well, I only have one reaction so far in my toolbox that can make a ketone. An acid catalyzed addition of water or a hydroboration oxidation to an alkyne, because that makes an enol, which tautomerizes into a ketone. So that's how you'll get your final product. But you also have to pay attention to the fact that this has 6 carbons in your product, and you only had 4 carbons to begin with. So you first have to make your chain longer. So that's the type of thought process that you're going to go through. There are 7 or 8 syntheses that the textbook finishes with. You'll notice every time it gives you an example, and then it gives you the answer, right? First, working backwards, that's a retrosynthetic arrow, right? Working backwards, and then it shows you the full synthesis. Because of the limitations in the virtual environment and drawing things out, I can't show you these things any better than the textbook already explains them. I'm happy to discuss them in class, but my recommendation to you, studying for your next exam, take every one of these syntheses and practice them. Work on this. Right? Figure out, how do I take an alkyne and form an aldehyde in this situation, right? And all the other problems that were presented in there between slides 73 and 90. That's going to be an incredibly useful, a good use of your time. Sorry, I got lost in my words there. And putting together your reactions from chapter 5, which is really just a hydrogenation reaction, chapter 6, and chapter 7. Here you see, right? Building a carbon chain, doing a Syn addition of hydrogen, stopping at the alkene, so I can then do an ozonolysis. And little things like that. So figure out how to incorporate all those reactions, try each one of them for practice first, right? Looking at a blank problem, And then if you still struggle with that, it's something we can discuss in class further. Okay, so that concludes chapter 7. My recommendations from this video specifically: know the different ways to add hydrogen, either hydrogen with palladium on carbon, hydrogen in the Linlar catalyst, or the dissolving metal reduction. 3 different important reactions there. Know the alkylation reaction. That's single-handedly the most important thing from this video. And then practice those examples of synthesis, and you'll be well on your way to succeeding in chapter 7. And simultaneously reviewing chapter 6, so you'll be in good shape for the final.